Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to learn how to construct and use a probability matrix. A probability matrix can help us organize our information in a probability problem and can help us visualize new insights. Let's start by constructing a 2x2 probability matrix, which is the simplest matrix. Suppose a study of mall shoppers has shown us that 70% of all shoppers use credit cards for purchases. In addition, the study reports that 20% of all mall shoppers use public transportation to get to the mall. Let's let C equal usage of credit card. And let's let T equal the use of public transportation. And we can summarize our percentages in probability statements by saying the probability of C equals 0.70 and the probability of T equals 0.20. We will recognize from our study of probability that these are marginal probabilities. Using these two marginal probabilities, we can begin to construct our 2x2 probability matrix. The 2x2 probability matrix has 4 cells, and the best way to construct it is to put one variable on each side. So we'll put credit card usage down here on the left, transportation at the top, and then yes and no for each category according to usage. Since 70% of our shoppers use credit cards, we can put the 0.70 over here in the margins, hence the name marginal probability, associated with the yes row in credit card usage. Under transportation, 20% of the people use public transportation, so we put that under the yes column. In the probability matrix, all the probabilities will sum to 1. This allows us to solve for the other marginal probabilities in the case of the 2x2 matrix. For example, if 70% of all shoppers use credit cards, then 30% of all shoppers do not use credit cards. And so we can put 0.30 here. If 20% of the mall shoppers use transportation, then 80% of the people do not use public transportation. So we can summarize what we have here with our marginal probabilities. The probability they have a credit card, or the probability of C, is 0.70. The probability they use public transportation is 0.20. But now we have 2 additional probabilities that we've just solved for. We've discovered that 30% of our mall shoppers do not use credit cards. We solve for that by taking the fact that the probabilities sum to 1 minus the 0.70 that actually use credit cards, resulting in this probability. In addition, because we know that 20% of all the mall shoppers use public transportation, we can learn from that that 80%, or 1.00 minus the 20%, do not use public transportation. That is, we can see from the bottom margin of our 2x2 probability matrix and from this equation that the probability that someone does not use public transportation is 1 minus 0.20 or 0.80 or 80%. The next question you may have is, what goes in these cells here? Why are they empty? Well, it turns out that the probability matrix is constructed of 2 of our 4 probabilities that we consider in the probability chapter. The 2 that make up or consist of the probability matrix are the marginal probabilities that we've already solved for, and the intersections or the joint probabilities which go in these cells. Suppose in our mall shopper problem, 12% of the shoppers use credit cards and public transportation. You might recognize from your previous study in probability that when we use the word "and," we're usually talking about joint probabilities or intersections. This statement can be represented in terms of probability symbols by the probability of credit card intersect transportation. And that equals, in this case, 0.12. Now, where does that go in our matrix? Remember, our matrix is made up of intersections. So this particular intersection or probability goes in what we sometimes refer to as the yes-yes cell. Yes, they use a credit card. Yes, they use public transportation. They do both of them. So we're going to put 0.12 in here. This is very nice in the case of the 2x2 probability matrix, because once you get one of the numbers in here and you have all the marginal values here, you can fill in the rest of the cells by subtracting from the marginal totals. In other words, if 12% of the shoppers use credit cards and transportation and 70% use credit cards, then by subtracting these two, getting 0.58, that is 0.70 minus 0.12 is 0.58. We've solved for this particular intersection, which is yes on credit card and no on public transportation. This particular cell is, they did not use credit cards, but they do use public transportation. You can see now that 12 from 20 is 0.08. So there is a 0.08 probability that a mall shopper uses public transportation, but not credit cards. Leaving us with this other cell, which if you take 0.08 and subtract from 0.30, you get 0.22. 22% of all mall shoppers do not use public transportation, and they do not use credit cards. We sometimes refer to this cell as the no-no or neither-nor cell. They don't use either one. You might also note that all the column probabilities must add up to the marginal column totals, and all the row probabilities must add up to the row marginal totals. So we've learned to this point that probability matrices consist of intersections in the cells and marginal probabilities in the margins. Another probability that we sometimes want to solve for is the union probability. Sentences asking about union probabilities or stating union probabilities usually use the words either or either or. Let's look at an example of that in this particular problem. Let's solve for the union of people that use credit cards or use public transportation, denoted by these symbols. In our probability matrix, this is relatively easy to solve for. We locate first all of our credit card users, which are in the first row, which sum to 70% or 0.70. Then let's locate all our public transportation users, which is located in the first column, summing to 20%. These are all the possible cases where there is a yes involved in a row or a column. Note that we have the yes row with credit card and the yes column with transportation. The only problem with this is that you might have noted that the cell that has the intersection of the two, the 0.12, was included in both the row and in the column, and therefore was double counted. So we can either do one of two things. We can either take the totals of the two marginal probabilities, that is, the row total for credit cards, which is 0.70, representing all these yes cells. We can take the total for the first column for transportation users, which is 0.20, noting that the 0.12 was included in each. We can subtract it out once so that we have a corrected probability. And that gives us a total of 0.78. So the union of using a credit card or using public transportation is 0.70 plus 0.20 minus the intersection 0.12, resulting in a probability of 0.78. And in effect, we've just used the probability formula for the union. There is another, perhaps more simple way to solve for union probabilities in a probability matrix. Recognizing that any element or cell that is a part of the union is part of a row or a column that has a yes in it, in this particular case, since we're doing the union of two yeses, if we select the three cells that are involved in yes column or yes row and merely add them up, we also solve for the union. So let's do that. 0.58, 0.12, and 0.08 also add up to 0.78, which is the union. So to summarize this particular way of solving for the union, merely add up all the cell probabilities that are included in either a row or a column that has a yes, and you will have the union of the yes, yes. There's actually a third way to solve for union probabilities, recognizing that this particular cell is what we call the no-no cell or the neither nor. The neither nor cell are all the people who use neither credit cards nor public transportation, which means they don't use either one of these. So if we take a look at this particular one, focus in on it, we know that 22% don't use either one. If we take 1, which is the total probability, minus the 0.22, which is the neither nor cell, we also are able to solve for the union probability. So in conclusion with the union probability, a person that belongs in the union, in this case a mall shopper, is someone who possesses either one or the other or both of the characteristics. The neither nor cell are people that possess neither characteristic and is the complement of the union. Another important probability that we often want to solve for using our probability matrix is the conditional probability. Conditional probabilities are not actually listed here as one of these numbers. We have to solve for it. So let's take an example. Suppose we want to solve for the probability that a person uses a credit card at the mall, given that they take public transportation. How do we solve for this using our probability matrix? Well, conditional probabilities have given statements or information that we already know. In this particular instance, we know that the person takes public transportation. It's a given. So in our probability matrix, we can go over here and box this in and identify this particular column because why? We know that the person is already one of these people. In effect, we could cross out the rest of the matrix. It doesn't really matter. This is the only part that matters anymore. So when we go to solve for this particular probability, we know that our denominator is going to be 0.20 because only 20% use public transportation, and we already know that our person uses public transportation. So the next question then is, out of the 20% that use public transportation, what proportion are people who are using credit cards? Well, our credit card users are right here. Of course, we have credit card users over here, but they are not in the public transportation column. Only 12% of all the people use credit cards and public transportation. So we take this particular value, 0.12, and put it over 0.20. The resulting conditional probability is 0.60. That is, we can say that 60% of all public transportation users at this particular mall use credit cards.